Welcome to Maths with EJD. In the previous video, I talked about zero-sum games, and we saw how we could use a mixed strategy, how we could use mixed strategies to solve zero-sum game. Of course, in a zero-sum game, we know that a player's loss is the gain for the other. A player's gain is the loss for the other person. So if a player wins one, it means the other player has actually lost one. If a player lost five, it means that the other player had gained five. That's what a zero-sum game is about. So in this video, my focus is on non-zero-sum games. And of course, as expected, a non-zero-sum a non-zero-sum game is a game in which the total payoff to all players does not remain constant. The total payoff does not remain constant. In the case of zero-sum game, it remains the total payoff is always constant, meaning that if you sum up all the payoffs, it ends up at zero, right? So a non-zero sum game is a game in which the total payoff to all players does not remain constant. What that simply means is that one player's gain, of course, one player's gain can be another's loss. Of course, that sounds like zero-sum game, right? But in the case of non-zero sum game, that is only a possibility. It is not necessary, but not necessarily. Okay. So this is really necessary in the case of zero sum game, but it's not necessary here. Okay. So if you consider like a 2 by 2 payoff matrix, so if we say in a 2 by 2 payoff matrix, we used that kind of thing uh for zero sum game. We use a 2 by 2 payoff matrix. So if we use the same kind of idea here, we'll see that it's also possible to consider it. All right. So in a 2 by 2 payoff matrix, each player, each player has two strategies. Each player has two strategies. Okay. And their payoffs, and their payoffs, and their payoffs depend on the strategies, on the strategies by both players. Of course, game theory in its very essence is actually that situation in which you have two players playing, and whatever they end up getting depends on both of them. All right. So by whatever I end up getting is not just dependent on what I do alone. It also depends on what my the other participant does, right? So payoffs depend on the strategies by both players. So the objective is to find the objective is to find an equilibrium. Need to find an equilibrium where no player, no player has an incentive, has an incentive to unilaterally, to unilaterally change their strategy. And that is the very definition of what we call the Nash equilibrium. Okay. So since you're talking about a zero-sum game, can we go for it now? Just like what we did the other time, except that now we are not talking about a you're not talking about a zero-sum game. Here, our focus is now on a non-zero-sum game where the loss of one is not necessarily the gain of the other. So again, we have player. So let's say we have two players. We have player A. We have player A Okay, let me still use player one. So we have player one with strategies A and B, and then we have player two. We have player two with strategies X and Y, just like what we had before. But except that here, it's no longer a zero sum. So here we have 3, 2. If player one uses strategy A and player two uses strategy X, then the payoff for for player one is 3 and the payoff for player two is 2. Then 1, 3, uh, 2, 1, and then 4, 4. Okay. So if you look at the values right there, that is actually a non-zero sum game because it's not like you have 3 minus 3, 1 minus 1, 2 minus 2, and 4 minus 4. So it's like player one is gaining 3 at the same time player two is gaining 2. For when player A plays strategy A and player two plays strategy Y, player one gains one and player two gains three, and so on and so forth. So that is why it is a non-zero sum game. Okay. So um player A can choose strategy A or B. Player one can choose strategy A or B, and player two can choose strategy X or Y. So can we solve now? Can we go for the solution? So let's go for the step one. Step one, we need the best response analysis. Best response analysis. Best response analysis. Okay. Now, if player B, if player So for player A, right? Let's start for player one, rather for player one. Let's see what happens. So for player one, if player two, if player two chooses, if player two chooses uh chooses strategy, let's start with strategy X, right? If player two chooses strategy X, so, we are looking for the best response for player one, right? So for player one, if player two chooses strategy X, so it means we are looking at this whole place, right? So for player one, if what player two is playing is strategy X, so player one can either play strategy A or B. So if player one plays strategy A, the payoff is 3. If you play strategy B, the payoff is 2. The payoff is 2. Okay. So in that case, we see that play okay, all right, so the payoff goes that way, right? But at the end of the day, we see that uh player one is better off with the payoff 3-2, right? If player two chooses strategy X, okay, um player one player one player okay, player one has three, three for A, right? Three for A and and two. Player one has three for strategy A and two for strategy B. That's basically what we're saying. And we know three is bigger, right? So that's one way. So automatically, in that case, uh, so so strategy A is preferred. Okay. Strategy A is preferred because because of the higher payoff. Because of the higher payoff. Okay. Because of the higher payoff. Okay. So now, if player B if player B now, rather if player two chooses, if player two chooses strategy Y. So in that case, see what happens. If player two chooses strategy Y, now we are here. Okay. And what are the payoffs for player one? The payoffs are one here or four here. Okay. So if player two chooses strategy Y, so player player one has the payoff is one for B. I mean one for strategy A and four for strategy B and four for B. So B, so B, uh, okay, so it's one for A and four for B. So B is preferred in that situation. B is preferred in that situation. Okay, so that's for player one, right? So we see that here, four for B will be preferred in that situation. So, I mean, we have those two situations now. Now, can we switch over to, let's switch over to player two. So for player two now, for player two, we want to see the best response for player two. For player two, again, we look at the situations. If if player one, if player one chooses strategy A, okay? If player one chooses strategy A, now we want to see player two's best response. So if player one chooses strategy A, that means we are here. Okay, I have cleaned up something. Yeah. Okay. So, all right. So if player one chooses strategy A, so we're actually here. So it means that B's payoff would actually be two and three. Okay. So, um, two and three. So if player one chooses A, uh, player two gets player two player two gets what? Gets two for playing X and three for playing Y. So two, player two gets two for X and two for X, right? And three for Y. And three for Y. So strategy Y is preferred. So strategy Y is preferred. Okay. Strategy Y is preferred because this is better. On the other hand, if player one, strategy chooses strategy B, so what happens if player one if player one chooses strategy B, okay? If player one chooses strategy B, so where we are at, so it means that player two would get one for X and four for Y. So um player two, player two, player two gets one for X and that's one for X and four for B. One for X, four for B. I mean, four for Y rather, four for Y. So Y is preferred. Okay. So how do we get the Nash equilibrium now? So a Nash equilibrium occurs when both players choose strategies that are best responses to each other's choices. So you see, for A before, we already had, you know, for A, so for A, we saw that we had, okay, I mean for player one, for player one, so we had A and B, but A was preferred, and in the other situation, B was preferred, right? Um, so it means that we have, okay, let me draw this again so I can, so I mean I've explained all of these things. I just want to draw this again to make it more relatable. So imagine that we have player one with strategies A, B, and we have player two with strategies X, Y, all this. So, and just like we said the other time, 3, 2, 1, 3, 3, 2, 1, 3. Then we now have 2, 1, 4, 4. 2, 1, 4, 4. Okay. So let's go. So imagine that for player one, right? We want to see the best response for player one. So if player two is using strategy X now, so it means player one would have um 3 and 2, and this is better, right? Then if player for player one, if player two uses strategy Y, okay, then it means player one would have 1 and 4, and this is actually better, okay? Those are the possible best responses for player one, okay? Can we switch it over and then go for, say, okay, let me change this marker to something else. So let me change it to this. So imagine for player two, now what are the best responses? So the best responses for player one are 3, 2, and 4, 4. So we want to see where they overlap, and that will be the Nash equilibrium. So I guess I think I should even write this. Determining Nash equilibrium, determining. So this is actually our step. Uh okay, we've talked about best response, right? Best response is step one here. Then we're going to talk, then the next thing should be the Nash equilibrium. Okay. So that should be our step two. So two, step two is Nash equilibrium. That's the next thing we are doing. And that's why I'm drawing this table again to drive the point home. I'm just repeating what has happened there. So if to get the best response for player one, if player two plays strategy X is 3, 2, because here he gets 3 and here he gets 2. So 3 is better. So that's why that has been circled. Okay. Then when player two plays strategy Y, the best response for player one would be the response for player one would so the payoffs are either 1 or 4, and 4 is better. So that's why I've circled 4, 4. So now focusing on player two now, if player one plays strategy A, okay, the best response for player two would, I mean, the response for player two are 2 and 3, but 3 is better, right? So let me use box for that. So I box this. Okay. So now if player one plays strategy B, okay. So the possible responses for player two are 1. The possible payoffs are 1 and 4. But 4 is better, right? So we also box that. So 4 is better, so I box this. Now, anywhere the initial pop, okay, I guess I want to make this better. So anywhere the initial purple color and the red circle coincide, that is your Nash equilibrium. I think that's a very nice way to put it. Okay. So talking about Nash equilibrium now, I can now say that know that a Nash equilibrium occurs when both players when both players choose strategies when both players choose strategies that are that are best responses to each other's choices. To each other's choices. Okay? To each other's choices. Now, what this simply means is that, okay, that's 1 point. So from the best response analysis, which we did above, from the best response analysis, okay, we know that player A, so player one rather, player one chooses player one chooses player one chooses A if player two chooses if player two chooses X, right? Then we also know that then player okay. Now, I mean, from the best response analysis, I think I just want to focus on the Nash equilibrium instead of repeating what we have done before. So, we have the Nash equilibrium already from what I already demonstrated up there. From the best response analysis, right? Player one chooses player one chooses B. All right. Player one chooses B if player two if player two chooses if player two chooses Y. Okay. And then you also see that player two chooses Y. Player two chooses Y if player one chooses B. So the key is that you see B, B, Y, Y. But Y, Y, that's basically the idea, right? Okay. So if player one chooses B, player two chooses Y. If player two chooses Y, player one chooses B. So that is exactly our Nash equilibrium. So we can now finally say that so hence BY, right? B for player one and Y for player two. BY, BY is a Nash equilibrium. It's a Nash equilibrium with payoffs. It's payoffs 4,4. So interestingly, they both get 4 points from the transaction. Okay. So now one question you may want to ask is mixed strategy important in this case? Well, the fact is that in this specific case, mixed strategies are not required to find the Nash equilibrium because the game has a pure strategy Nash equilibrium at BY. So mixed strategy is totally not required. All right. So okay, maybe I think I want to add that point. So in this case, mixed strategies are not required, are not required since the game, since the game has a pure strategy, That is without using all those probabilities now. We have a Nash equilibrium. So in this case, mixed strategies are not required since the game has a pure strategy Nash equilibrium. Nash equilibrium at BY. Okay. Of course, which gives 4-4 for sure. So both players are best responding to each other's choices, and no player has no incentive to unilaterally change their mind. Of course, mixed strategies might be required in other games where pure strategy Nash equilibrium do not exist or are hard to identify. So when mixed strategies are needed, that is if there's no pure strategy Nash equilibrium and there is indifference between strategies, like maybe when players are indifferent between their available strategies, they don't care, they can just randomize their options. That is, in those cases, you can say you need mixed strategies. But if you can get a pure strategy in Nash equilibrium, mixed strategies are totally not required. So to conclude this, now, uh, so conclusion, the Nash equilibrium, the Nash equilibrium for this game occurs at by equals 4, 4. All right. Okay. So at this point, neither player can improve, neither player can improve their payoff by unilaterally changing their strategy. And that's it. So in the next video, I'll be talking about what is known as the general sum game. We've talked about zero sum game, non-zero sum game. So in the next video, I'll be talking about the general sum game. So if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And of course, like and share so that more people can have access to this great learning. Till next time, bye.